All right, let's start with a really cool puzzle from World War II. Picture this. You're an Allied commander. Your entire strategy, everything you're planning, depends on one crucial piece of information. How many tanks is the enemy actually producing every month? But how on earth do you count something like that? I mean, these tanks are hidden. They're deep inside enemy territory. Well, you might think the answer involves spies, right? Secret agents, high-risk missions, but no. Amazingly, the answer comes from an idea that had been just kind of kicking around for almost 250 years. An idea first jotted down by a quiet English minister. And this idea, it would go on to become one of the most powerful intellectual tools, maybe ever. So today, we are unpacking that exact secret weapon. We are talking about Bayesian thinking. At its heart, it's really just a formal system for updating what you believe when you get new information. And it's a tool that's so powerful, it can take you from counting those hidden tanks all the way to the absolute cutting edge of modern research. Okay, let's dive right into that high-stakes mystery I mentioned, the German tank problem. And you've got to understand, this was not just some academic puzzle. I mean, the lives of thousands of soldiers were literally on the line. They had to get this right. So here's how it all went down. You had your traditional intelligence, spies on the ground, reconnaissance photos, and they were all saying that German factories were churning out something like 1,000 tanks a month, a huge number. But then you had this small group of statisticians, and they tried a totally different approach. Their only data, just the serial numbers from a handful of captured tanks. And their estimate was wildly different. They said it was closer to 250. And the craziest part, after the war, when they got their hands on the actual German records, it turned out the statisticians were almost spot on. So, the big question is, how? How in the world did they do that? How did they manage to see the entire picture from just a few little puzzle pieces? Well, to really get it, we need to bring this whole thing down to a much smaller scale. We're going to go from the battlefield right to the kitchen counter. Right. To really wrap our heads around the logic here, let's use a super simple analogy. Let's forget about tanks for just a second and think about cookies. Honestly, this is the best way to build an intuition for this core idea. Okay, imagine you've got 2 bowls of cookies in front of you. You know exactly what's in them. Bowl 1 has 30 vanilla and 10 chocolate cookies. Bowl 2 is a perfect 50-50 split, 20 of each. Now someone picks a bowl completely at random, reaches in, and hands you 1 cookie. You look down, and it's a vanilla cookie. So the question is, which bowl did it probably come from? I mean, your gut instinct is probably screaming bowl 1, right? It just feels more likely. But how much more likely? And that's exactly where Bayes' theorem comes in. Think of it like a formal recipe for updating your beliefs. You start with what you believed before you saw anything new. That's called your prior. For us, since the bowl was picked at random, our prior is simple, a 50-50 shot for either bowl. Then you get the new data, the vanilla cookie. That's your evidence. The likelihood is just the chance of getting that specific evidence from each bowl. And when you put it all together, you get your posterior. That's your new, updated belief after you've seen the cookie. So let's actually walk through the numbers here. We start with our priors, right? A 50% chance, or 0.5, for each bowl. Now, the likelihood. What's the chance of drawing a vanilla cookie if it is bowl 1? Well, that's 30 out of 40, so 75%. And from bowl 2, 20 out of 40, so 50%. So you multiply the prior by the likelihood for each bowl, and then you do a little step called normalizing to make sure it all adds up to 100%. And there you have it. After seeing just that 1 vanilla cookie, our belief has shifted from a 50-50 guess to a 60% confidence that the cookie came from bowl 1. Look, the really important thing to get here isn't the cookie math itself. It's this. Bayes' theorem gives us a kind of mathematical engine for learning. It's a formal process that takes what we used to believe, combines it with what we see now, and tells us what we should probably believe next. All right, so now let's take this simple rule, this cookie logic, and see how it scales up. Because it can be used to solve some unbelievably complex and diverse problems, taking us right back to our World War II mystery and even into the world of modern medicine. This is where you really see the incredible versatility of this way of thinking. So for the German tank problem, the hypothesis isn't which bowl the cookie came from, it's the total number of tanks being produced. And each serial number you find is a new piece of evidence that updates that belief. Think about it. If you capture a tank with serial number 60 on it, you know for a fact that there are at least 60 tanks. Right away, your belief that there are only, say, 50 tanks goes to 0. It also makes a total of 10,000 tanks seem a little less likely. But you can apply this exact same logic to estimate the number of bacterial species in a human navel, or to build models that predict airline flight delays, or even to figure out if a kidney tumor most likely developed during a veteran's military service. It's the same core engine every single time, just pointed at a different problem.
Now, a really common question people have is, wait a minute, isn't this all just subjective? I mean, it all depends on what your starting belief is, right? And you know what? That's true. But here's the magic part. With enough data, it actually doesn't matter that much where you start. This concept is called swamping the priors. You could have two people who start with wildly different assumptions, but as they both see more and more of the same evidence, their updated beliefs, their posteriors, are going to get closer and closer together. Eventually, the data just speaks so loudly that it drowns out those initial assumptions.
Okay, so in the modern era, things have gotten even more interesting. You see, powerful computers have totally transformed Bayesian thinking. It's not just about a single calculation anymore. It's evolved into a full-blown philosophy for learning from data step by step, or iteratively. So the modern workflow basically looks like this. Step 1, you build the simplest possible model you can think of that might explain your data. Step 2, you check it. You run it against your data and you actively look for where it fails, where it just doesn't fit. Step 3, you use those failures as a roadmap to improve it. You refine it, maybe add a little complexity right where it's needed most. And step 4, you repeat the whole cycle. And with every single loop, you learn more, not just about your model, but about the data itself. And this iterative computational approach is incredibly empowering. As the author Alan Downey puts it, it provides such a short path from a basic introduction to the research frontier. In other words, once you get the hang of this workflow, you can start tackling really complex, cutting-edge problems much faster than you think. All right, so let's bring this all together. What are the big key ideas you should really take away from this whole way of thinking? First up, embrace your uncertainty. Don't just say, I'm not sure. Actually try to put a number on it. Second, have a system for updating your beliefs. Don't just change your mind randomly. Do it based on evidence. Third, think iteratively. Start simple, check your work, and then build up from there. And finally, a really important one. You could call it a pro tip. It's sometimes called Cromwell's rule. Never, ever assign a 0% probability to something unless it's truly impossible. Because if you say something has a 0% chance of being true, then no amount of evidence, no matter how overwhelming, can ever change your mind.
When you get right down to it, Bayesian thinking isn't just for statisticians or data scientists. It's really a framework for clear thinking for all of us living in a really uncertain world. It's a challenge, really. A challenge to be honest about what we think we know and to be disciplined about how we change our minds. Which, I think, leaves us with one last question to chew on. What is one belief you hold right now that you'd be willing to change if you saw the right evidence?